This mini-challenge addresses the problem of autonomous navigation under conditions and visual constraints. The mobile robot must reach a series of predefined waypoints while responding to visual signs, specifically color cycles representing traffic lights. The team designed and implemented a modular ROS two-way control system. The robot stops when a red object is detected, slows down when it detects yellow, and moves normally on a green detection. The approach integrates color detection, odometry-based localization, and a waypoint controller and path planning.
The solution is divided into four primary nodes: path generator, controller, odometry node, and color detector. The path generator node reads a list coordinated from a jam file and publishes them sequentially into the goal topic upon receiving a next goal trigger. The odometry node estimates the robot's pose using differential drive kinematics. It subscribes wheel encoder data into the published pose2D messages to the pose topic. The controller node receives pose and goal messages and implements proportional control. It computes the linear and angular required to minimize distance and orientation errors, control gains, and defines parameters. The controller also responds to an integer signal published the color detector. 3 equals to red stop, 2 equals to yellow slow, and 1 equals to green move. The color detector node processes the camera feed using OpenCV. It extracts the contours using HSV-based trace holding and CAN-EH detection. It publishes a discrete signal depending on which color is detected. All nodes are launched together using pathlaunch.py and configured via pathparams.jam.
This section demonstrates the robot's behavior on the 4 different goal points: 0.3, 1.0, 1.0, 2.0, 1.7, 2.0, and 2.0, 0.0, defining the jam configuration file. The robot successfully navigates to each goal. During the trial, red, yellow, and green circles are placed in the field of view. Upon detecting red, the robot immediately stops as expected. With yellow, the linear velocity is reduced to the 50%. When green is detected, normal movement resumes. Terminal outputs confirm color detections and velocity modulation logs. Goals emerge on the ground and validate visually. The CMD bell topics shows velocity suppression and reception aligned with the color signals.
The controller was tuned using the Siegel-Nichols-inspired trial method for first-order systems. Initially, linear and angular gains were set to 0 and then gradually increased. The selected values, Kp, achieved conversions within 2 seconds at each waypoint without overshoot. A tolerance of 0.15 meters was defined for goal acceptance. Performance was evaluated using root mean square error, RMCA, within the robot's estimate position and goal coordinates. Across the waypoints, the average RMCA was 0.076 meters. This suggests the controller achieves sufficient accuracy for typical indoor navigation. The robot's behavior is consistent with expected outcomes, holding on red, slowing on yellow, and moving freely on green. However, the system shows sensitivity to lighting, especially for pale yellow hue detection. The control strategy's main advantage is the simplicity and fast tuning, but it lacks robustness to dynamic disturbances or sensor noise. This task demonstrates a functional reactive controller for a differential drive robot using modular ROS nodes. The integration of image-based state transition and proportional control enables basic context-aware navigation. From a control theory standpoint, this proportional-only method is suitable for slow-speed robots in node environments. Thus, future work may benefit from closed-loop position feedback, adaptive gains, or state observers to improve reliability.